Okay, so question 2 was primarily focusing on collisions and impulse. Question 2, paper 2, starting. So in this case, it was asking us to calculate the speed of the ball as it leaves the racket. So I've been given different bits of information in the question. So I've been given a graph. I've been told that the area under this graph, so this area here, was equal to 0.84. I've got force on there and I've got time in milliseconds down here. So in this case, what we should remember is that the impulse is the area under the graph. Now, impulse is equal to the change in momentum. So in this case, momentum is the area under this graph. The change in momentum in this case is going to be mv minus mu. With our initial velocity becoming 0, so our change in momentum, our initial momentum is also 0. So I can also say that this is equal to the final momentum. So final momentum, mv, is equal to 0.84. So then rearrange to have v as my subject. I've got 0.84 divided by the time, not divided by the time, divided by the mass, which was 5.8 times 10 to the minus 2, giving me 14.5 meters per second. For question B, so the second part of this one, it then said a show question, show that the average force exerted on the tennis racket is about 50 newtons. So again, I'm going to use my force, change in momentum, change in time equation. In this case, I've got the change in momentum, that's 0.84, as I have got from the previous question and from the graph. But my change in time, I needed to actually calculate this. And so what I needed to do is interpret the graph here. Okay, so when I looked at it, I kind of went and here and said, okay, that's about where it's lost contact. So that was 28. And around here is when it started contact was about 12. Okay, so I did 28 take away 12. Remember, it's milliseconds. So I had to do times 10 to the minus 3. And that gave me around about 53 newtons, which is approximately 50 newtons. If you didn't read off those values, let's say you'd read like 27 and you'd read 13, that's okay. They gave you a range here that they would accept it to be between, say, 14 to 16. The next one then says, determine with reference to work done by the average force the horizontal distance travelled by the ball whilst in contact with the racket. So we go to our work done equation. Work done is equal to force times displacement. Okay, in this case, the work being done, all right, is also equal to the kinetic energy of the ball, so a half mv squared. So I just worked that out using my mass and using my velocity I calculated in part A to get 6.09. Okay, carried that and left that in my calculator. Displacement is work done divided by force. So in this case, I used my answer from above. Again, I used 53. You could have used 50 if you wanted, or if you had a different value. So I kept my calculator value in and then just divided it by 53 to get 0.115, which is around about 0.12 meters. The last one then was drawing a graph to show the variation with t against the velocity of the racket. So with this one, we know that the velocity is increasing, but it isn't increasing linearly. Initially, it's going to be accelerating, and then it's going to start not like decelerate, kind of beginning to decelerate in terms of its acceleration. So if we're looking at this, we can also see that we've got the force being increased and then the force is being decreased. So yeah, we have our acceleration and then we have it decelerating as it goes through there. So we have the curving up and then coming back off.